Okay, so let's start. Today we talk about the last important chapter for this class, which is chapter 6. It is called hypothesis testing. Okay. So hypothesis testing is similar to chapter 5, which is confidence interval. Okay. Remember we discussed one of the example in chapter 5 about the micro drills. Okay. In the micro drill example, we want to check how many drills micro drill can drill before it fails. Okay. And we have several samples and get the sample mean of 12.68 holes, which means it can drill 12.68 holes on average for these samples before the drill fail. Okay, and also tells us a standard deviation of 6.83. Okay, so let's see. We want to know this question. The main question is whether or not the population mean lifetime mu is greater than 11, which means if these new micro drills can, on average, drill more than 11 holes before it fails. Okay, so this is very common questions. We want to know how many holes this drill can drill on average. Okay, a certain product can last how long. We can address this question by examining the value of the sample mean, okay, which is 12.68 holes on average. So 12.68, the sample mean is larger than 11, okay, but there's uncertainty in the sample mean. So we cannot guarantee the population mean is actually larger than 11. So we would like to know just how certain we are about the mu, which is population mean larger than 11, even though we got a sample mean larger than 11, but how sure we are. Okay, so in this case, we do not really need the confidence interval. Remember, in confidence interval, we give something like this. So we say, for example, 95% confidence interval of the population mean is between a range, for example, 10.75 to 14.47. So we have 95% confidence the population mean is between this range. Okay, but we are not really interested in that. We are interested in if the mean value is larger than 11. Okay, so statement about the mean value larger than 11 is an example of hypothesis. Okay, so this hypothesis is about the population mean value of mu. Okay, to determine how certain we can be that his hypothesis is true, we need to perform a so-called hypothesis test. Okay, confidence interval is not same as hypothesis. So chapter 5 is not the same as chapter 6, of course, but these two are very similar. Okay, so confidence interval is similar to hypothesis test. Okay, actually, if we can do confidence interval, we can do the hypothesis test for a certain question. And same thing, if we can do hypothesis test for one problem, we can do confidence interval for the other. Okay. Section 6.1 is a large sample test, which is hypothesis test for population mean. Remember section 5.1. 5.1 is large sample confidence interval for a population mean. Okay, so the setup is the same thing for the first section of chapter 1, chapter 5, and chapter 6. Okay, And the next couple of slides will introduce some new definition, new words. Okay. The first one is called null hypothesis. Okay. Another name for that is H0. Okay. So what is null hypothesis? Assumed to be true until we can prove otherwise. That says the effect indicated by the sample due only to a random variation between the sample and the population. Okay, so in other words, H0 means the sample does not reflect population information. Okay, so sample does not reflect population information. Okay, in the previous example of microdrill, the sample mean is 12 pound something. Okay, so sample does not reflect population information means the population mean will not be equal to 12 pound something, the sample mean. Okay. Then we have alternative hypothesis, okay, which will be accepted as true if we can disprove H0. Okay. So H0 says, H1 says the effect indicated by the sample is real. Okay, which means sample does reflect population information. Okay, so another name for alternative hypothesis is H1. Okay, so H1 means sample reflect population information. In the previous example, that means the sample mean of 12 pound something actually reflect the population mean, means the population mean is almost the same. So in performing a hypothesis test, which we'll discuss in next moment, we essentially put the null hypothesis. The null hypothesis is H0 on trial, okay, to check if H0 is correct or not. All right, we have some new words here, a test statistics and the p-value. Okay, this is especially the p-value is new here. A single statistics calculated from the sample which allows to reject or not reject H0. For example, we calculate a z-value. We know z-value very well right now. This is based on the z-table from table 8.2. Okay, so z-value is an example of statistics. So we calculate that value. Okay, and then we calculate a probability which is based on the z-value or other test statistics that measure whether the test statistics is likely or unlikely if we are assuming H0 is true. Okay, so it's kind of hard to understand now, but it is not that difficult. You will see in a moment. Another new word is called rejection region. Okay, so rejection region is a rule that tells us for which value of the test statistics, for example, the z-value, or for which p-value the null hypothesis should be rejected. Okay, so this is another new word we're going to discuss much more in a moment. Section 6.1 is large sample test for population mean. Okay, we need to draw a certain conclusion. There's two possible conclusions. One is reject H0, or we fail to reject H0. Okay, if we can not reject H0, we should conclude H1 is true, which is alternative hypothesis. We also need to state reliability of our conclusion. Okay, that reliability is the p-value. The p-value. So how do we decide when to reject H0? So this is by comparing the p-value with a so-called significance level, alpha. Okay, so we'll compare the p-value with the alpha. The alpha is the maximum tolerable risk we want to have of making a mistake. Okay, typical value for alpha is 1% or 5%. Okay, most likely the question will tell us the alpha, but sometimes the alpha is not mentioned in the question. In that case, we're gonna use 5%. 5%. Then let's look at an example, okay, to have an idea of what these new words mean. So let's say a mayor of a small city claimed that the average income in his city is $35,000 and the standard deviation of 5,000. Okay, so we take a survey, we take a sample of 64 family and find out the average of these 64 family, the average income is only $30,000. Okay, so much less than the claim of the average, which is 35. So we want to know if the claim of the mayor is correct. So we need to set up a hypothesis. Okay, the null hypothesis H0 is set up as if the mean value of the mu, which is the average income of the city, is $35,000 actually. Okay, which means the mayor's claim is correct. Then H1, which is alternative hypothesis, will be the opposite, which is the mean value is not equal to $35,000, or the mayor is wrong. Okay, so let's start by assuming H0 is true. So the mean of the population will be $35,000. Okay, remember we set up H0 as the sample does not agree with the population. All right. So to have an idea of the population mean, we want to know about the population mean is $35,000 or not. We need to look at the sample mean. Okay, the sample mean tells us $30,000. Based on central limit theorem, which is section 4.11, we know when the sample size is large. Here the sample size is 65, so that's large. The mean value will follow a normal distribution with a mean value of 35,000 because we assume the claim is true. Okay, we want to check whether the population mean is $35,000 or not, and then the standard deviation will be this because based on central limit theorem, that will follow a normal distribution with a mean value of $35,000. Okay, this is equal to the sample standard deviation divided by square root of sample size. So it's 5,000 over square root of sample size is 64. So that's 625. Okay, so this is a normal distribution. If we assume H0 is true, the population should follow. And there's a name for that. It is called null distribution. Because if we assume the null hypothesis is true, that is the distribution the population should follow. Okay, should follow. All right, so remember the sample mean is only $30,000. Okay, if we assume the claim is true, that should follow a no distribution. So we calculate the z-score. The z-score, we calculate that based on chapter 4, the z distribution, the normal distribution, right? So we calculate z-score for $30,000, okay? And the z-value is -8. Remember the z distribution? So -8 is right here. It's very small. So the chance we observe a $30,000 if we assume the null hypothesis, no distribution is true, is very small. It's very small. It's -8. So the probability of observing a sample mean of $30,000 very far away from the mean value of 35. Okay, 35. Which is we are assuming H0 is true, is nearly 0. Okay, so 8 standard deviation away from the mean is nearly impossible. Okay, remember for 3 standard deviation is 99.7%. Okay, for -8 is much less, nearly 0. So normally speaking, values more than 3 standard deviation away from the mean are considered extremely unlikely. Okay, for normal distribution, that means 99.7 chance it is within 3 standard deviation. Okay, so more away from that is very unlikely. Because the observed sample mean of $30,000 is so unlikely, if we assume the mean value is 35,000, so we choose to reject H0, which is the population mean is $35,000. So we conclude that the mayor's claim is incorrect, okay, because the mayor claim the city's average income is $35,000. If he's right, then the chance is nearly 0. So we conclude that he's not right, incorrect. All right, so this is a sample of hypothesis test. Okay. For this section, we talk about large sample test for population mean. If the sample size is large or equal to 30, is the mean value of mu and standard deviation of sigma. Okay. If the sigma is null, we use sigma, which is population standard deviation. If the sigma is not null, we can use S, which is sample standard deviation for sigma. And then we set up H0 and H1. Okay, we define H0 and H1. We let the population mean equal to a certain value. We call that mu0. So mu0 is the value we want to check. For example, $35,000. Okay, and H1 will be opposite of H0. Okay, if H0 is mu equal to mu0, then H1 will be the opposite, which is mu not equal to mu0. Okay, so we define H0 and H1. And then we calculate statistics. In our case, we calculate the z value. Okay, so that's the equation is not very correct. It should be this. Okay. All right. Okay. So all equal to sample mean minus mu0. The value we want to check. S is the sample standard deviation. N is the sample size. Okay. So we calculated the z-score. The z-score based on this equation. Okay. Because the population, the sample mean has follow a normal distribution based on central limit theorem. Okay. Okay. With the mean value of mu0, which is the value we want to check, and the standard deviation of this or this. So we calculate the z-score based on this equation. If H0 is actually true, then the value of x should be close to mu0, should be close to mu0 here. Okay, and z value will be close to 0. Okay, z value will be close to 0. If H0 is not correct, then sample mean x will be much larger or much smaller than the mu value. Okay, so the z value will be much larger or much smaller than 0. Okay, indicating we should reject H0. Right. So in the red zone, it's called rejection zone. Okay, because the z value is either too large or too small. Okay. So after we calculate the test statistics, such as the z value, we calculate the p value, which is based on, for example, table 8.2. Okay, so p value is defined as here. So the probability of observing just by chance that a test statistics, okay, in our case here is the z value as extreme or even more extreme that we actually observed. Okay, so if H0 is rejected, this is actual probability that we made an incorrect decision. Okay, it's kind of awkward statement, maybe hard to understand, but its p-value is actually the probability, okay, that we make incorrect decision if H0 is rejected. Okay, the smaller the p-value, we should more likely to reject H0. If this probability is small, if the p-value is small, smaller than a certain pre-assigned significance level alpha, so if p is less than alpha, then we just reject H0. Okay, and then we conclude H1 is true. All right. Okay, so let's talk about the procedure again. First, we need to assume H0 is true. Okay, this is similar to begin a trial by assuming a defendant is innocent. Okay, so we assume H0 is true, and then we look at the sample. Okay, and based on the sample, we do the hypothesis test, okay, which is measuring the strength of disagreement between the sample and H0, okay, to produce a number which is called p-value. So p-value is a probability which is between 0 and 1. Okay, so we calculate p-value. And here is important p-value is what? P-value actually is the possibility of H0. Okay, so if p-value is very small, for example, if p-value is 0.0001, so the probability of H0 is only 0.001. Okay, the possibility of H0 is true is very small, then we're gonna reject H0. So we can conclude H1 is true. Okay. So the smaller the p-value, the stronger evidence is against H0. Okay. If the p-value is sufficiently small, okay, how is sufficiently small? That is p less than alpha. A typical value of alpha probably will be 5% or 1%. Okay, if p-value is small enough, then we assume assumption of H0 will be not correct. So we abandon H0 and we believe H1 is true instead. Okay, and we call this process rejecting the null hypothesis. So rejecting H0. All right. So the steps, again, first we define H0 and H1. We're gonna show you a couple of examples how to do that based on what the question give us and what the question ask. Okay, and then we assume H0 is true. Okay. The next step is we calculate a test statistics in section 6.1. That will be the z-value. Okay, and based on the test statistics, we assess the strength of the evidence against H0, which is the p-value. Okay, so we calculate the p-value based on the z-score or other test statistics. Okay. The p-value again is probability if we assume H0 is true, that the test statistics will give a value whose disagreement with H0 is as great or greater than what actually observed. Okay, so again, this is long sentence. Okay, so just remember the p-value is the probability assume H0 is true. Okay, there's another name for p-value, which is observed significance level. Okay, so we compare p-value with alpha and draw a conclusion. If a p-value is less than alpha, we're gonna state a conclusion. Then we reject H0. Okay, so that's the procedure to do a hypothesis test. Okay, another example. Okay, so here a daily yield for chemical plant average 880 tons for several years. We have control engineer manager want to know if the average has changed. Okay, so she take a sample of 50 days and record average, which is 871 tons. Okay, so close to 880, but not too far away. Also, she calculated the standard deviation of 21 tons. Okay, she want to know if the average has changed. Okay, so based on that, we set up H0 and H1. Okay, so we set up H0 is mu equal to 880, and H1 will be mu not equal to 880. Okay, so typically we're gonna set up H1 as what the question is asking. So the question is asking if the average has changed. So that one of the reason we set up H1 is not equal to 880. So changed. Another rule or tip is the equality line always go with H0. H0. All right. So we calculate the z-value. Okay, the z-value is the mean value minus mu0 divided by this. Okay. The sample mean is 871, right? And okay, the mu0 is 880. Sample standard deviation is 21. Sample size is 50. Okay, so we calculate z-score is minus 3.03. Okay, so more than 3 standard deviation less. And then we calculate the p-value based on the z-score. So we are very familiar with the z-table already. Okay, so the p-value is the probability that the z-score is more extreme or could happen just by chance. Okay, the p-value for z-score further away from 3.03, which is larger than 3.33 or even smaller than minus 0.03. Okay, so based on the z-table and table 8.2, okay, so we can calculate the p-value. Okay, which is around 0.0024. Okay, so very small. Okay, so the p-value is less than alpha. Okay, the question doesn't tell us alpha. Believe in this question. Okay. So we choose our own alpha, our own significance level. Let's say we choose 1%. Okay. If the p-value is less than alpha, so our p-value is 0.0024, then we reject H0. Okay, and we say the results are statistically significant at level alpha. Okay. The p-value is larger than alpha, we do not reject H0, and we see the results are not significant at level alpha. Okay, so anyway, we compare p-value with alpha. If p less than alpha, then we reject H0. Okay, so we see H1 is true. Otherwise, we cannot reject H0. Okay, so because p in this case is less than alpha, so we reject H0 and conclude that H1 is true, which is the average yield has changed. Okay. Go back to here. We just conclude H1 is true, which is the average has changed, which is not equal to 880. Okay. So this is H1 is true. All right. So we compare the p-value with alpha, and actually that's another method which is by using the rejection region. The rejection region we just give the definition in the previous slides. Okay. So if alpha, let's say, is 0.01, so what would be the critical value that mark the dividing line between the rejecting and not rejecting A0. Okay, because we know if p-value is less than alpha, then we reject A0. P-value less than alpha, we do not reject A0. Okay, so the dividing line will be p-value equal to alpha. Right? So, and we call that critical value of the test statistics. Okay, so the critical value in the previous example will be half alpha equal to 0.05. So the alpha will be equal to 0.01. Okay, so based on that, the critical z value will be 2.58. So this is again based on table 8.2. Okay, so we calculate the z score for the half alpha of 0.005. Okay, so we know how to do that based on chapter 4. Okay, so the reject region in that case will be plus minus 2.58. Okay, so if the z score fell in the reject region, which is the red area, is two red areas, okay, its p-value will be less than alpha of 1%. Okay, in the previous example, the z value is actually within the region, which is minus 0.33, which is here, somewhere here. Okay, so it fell in the rejection region, so we reject H0. Okay, so normally we do not use the rejection region, so instead we just compare the p-value with the alpha. All right, so one-tailed test. Okay, what we discussed, we give two tails, upper and lower. So that's two tails on the two ends. Okay, sometimes we only interested in one tail. Okay, we are, for example, we're interested in detecting the specific directional difference in the value of mu. We can set up H1 and H0 like this. Okay, H1, we can define mu value larger than certain value or smaller than certain value. Okay, and in that region, in that case, the rejection region will be on one hand, either the right or the left hand tail. Okay. All right, so let's look at example of one tail test. Okay. Homeowner have a sample of 64 homes. Okay, this is a large sample similar to her own, and found that the average is this much, and standard deviation is 15,000. Okay, the question is asking, is this sufficient evidence to conclude that the average selling price is greater than $250,000? Okay, alpha is given as 1%. Okay, so how to set up H0 and H1? I will look at the last sentence and look at what the question is asking. The question is asking this: the average selling price is greater than $250,000. So that will be H1. Okay, so mu value of the population is larger than 250. Okay, so H0 will be the opposite. So H0 will be less or equal to 250. Another rule is, remember, the equality line always go with H0. Okay, so remember that. So based on what the question is asked, And the equality line go with H0, so we can set up H0 and H1 like this. Okay. And then we calculate z-score. Okay, we just plug in the number. Okay, we calculate z-score is 1.07. Okay. So after we calculate z-score, we can either use the critical value approach or the p-value approach. Okay, let's look at the critical value approach first, which is less commonly used compared with the next one. Okay, so the rejection region based on alpha of 0.01 is 2.33. So we reject A0 if z-value is larger than 2.33. In our example, the z-value is not larger than 2.33. It's 1.07. It's here. Okay, so it does not fall in the rejection region. So H0 is not rejected. Okay, so what we conclude is we conclude that's not enough evidence to indicate that the population mean is greater than 250. Okay. Or we use the p-value approach. Okay. In this approach, we calculate the p-score, the p-value. Okay. The p-value will be the probability for z-score larger than 1.07. Okay. So that is based on table 8.2. Okay, because table 8.2 only tells us the value on the left-hand tail. Okay, so this value we got from the table 8.2. So we use 1 minus that value. So because we are asking on the right-hand tail. Okay, so the p-value is 0.1423. So we compare the p-value with the alpha. Alpha is 0.01. So the p-value is much larger than alpha. So we cannot reject H0. So H0 is not rejected. So we say there's insufficient evidence to indicate the mean value is greater than 250. So we cannot conclude H1 is true. Okay, so this is another example. Okay, so let's continue for a couple of more slides. Okay, so the critical value approach and the p-value approach, which we just discussed in the previous two slides, will give the same result. Okay, but p-value is more used because of the following reason. The one is the computer printout normally will calculate the p-value. Okay, and after we calculate p-value, we can compare the p-value with any alpha, any significance level we choose. Okay, so we just calculate the p, compare with alpha, and alpha can change. So we have more freedom for the p-value approach. Okay, what should we do if we are the experimental and no one give us a significant level alpha to use? Okay, then we can just choose our own alpha. Okay, so normally if the p-value is less than 1%, so that is easy. We just reject A0. Okay, so the results are highly significant. Okay, if the p-value is between 1 to 5%, we can also reject H0. Okay, and we call that statistically significant. All right. But if the p-value is between 5 to 10%, then we cannot we cannot reject A0. Okay. We can state results are tending toward significance, but we cannot just reject H0. Larger than 10%, we call that not statistically significant. And of course, we cannot reject H0. Okay, so we can say 5% is the cutting point. Less than 5%, we can just reject H0. Okay. So more than 5%, we cannot. Okay. I think let's just stop here for today. We're going to continue next time.